In the study, I previously implemented the list class, which is based on the classic linked list structure, and the refined list class, which provides faster insertion operations by allowing direct access to the last node. Now I'm creating the list test class to really test the functionality of both classes. This test program will perform insertion, deletion, and listing operations, display the results, and compare their performance by measuring execution time on large data sets. And my previous codes are here. Now in here I am creating a list of type integer using the list class. This operation initializes the list starting a node to null and its length to 0. By ensuring type safety, only integer values can be added, allowing operations such as insertion, deletion, and listing to be performed on the list. In this code block, uh, the numbers 1, 2, 3, and are sequentially added to a list. And then the number 99 is inserted at the second index of the list. After that, the number 99 is removed from the list, and the size of the list is printed after each operation. First, the size of the list is displayed after the additions. Then the removed element is printed during the removal process. And finally, the updated list size is shown. Not shown. In here, first we add 1 to the list in here. This operation has a time complexity of O1 because the element 1 is added to the end of the list, and this operation happens is in constant time. Uh, for 2 and 3 are same. Add the we add to the end of the list. For here in here we add 99 to the second position of the list. This operation has a time complexity of O(n) in the worst case, because before adding 99 we need to shift the elements 3 and 2 one position to the right. This operation requires shifting all elements after the insertion point, so in the worst case, the time complexity is O(n). Um, in here, first I add the values 10, 20, and 30 to the list sequentially using list, a refined list add method. These operations have a time complexity of O1 since they add elements to the end of the list. Um, then, um, then in here, um, to insert the value 99 at index 2. This operation requires shifting elements to the right, so in the worst case, it has a time complexity of O(n). And in this line, I print the size of the list after addition operations. And in this line, removes the element at index 2 from the list and displays the removed value. Uh, since elements need to be shifted, this operation has a worst case time complexity of O(n). Then in here, it prints the size of the list after the removal operation. In here, I use a compare implementation method. Inside the method, I define int n equals 100 to specify a list of 100 elements for testing. Then I declare long start time and end time to store the start and end times for measuring execution duration. This way, I will compare the performance of different list implementations. And here in this line, um, I catch the current time in nanoseconds before starting the operation. Then in the for loop, um, adds the all values from 1 to n to the list. Since each addition is done at the end of the list, the time complexity is O1. If a tail reference is used, otherwise it averages to ON. Uh, after uh, after the loop completes, um, we use this line to record the time when the operation ends. Uh, and finally, in this line, um, it prints the total time taken for the addition operations in nanoseconds. This value indicates the performance of adding n elements to the list. And, and make we will do the same thing for a refined L list. And we get these results. And our all results are here. In the for loop, I add values from 1 to n sequentially to the list. Each addition happens at the end of the list. So if the list has a tail reference, it runs in O1 time. Otherwise, the average time complexity is On.